We're joined today by special guest Jon Forster. We're talking about microwave technology. Jon, just want to welcome you first of all. Welcome to the conversation.
Thank you, Lori. Thank you, Adam.
And I just want to, Jon, if you could just start off by just introducing yourself, giving us a little bit of an idea of your background and your experience and skills.
Certainly. My background is I did an undergraduate degree in mining engineering at Queen's University in Kingston, Ontario, Canada. And then I followed it up with a master's in mining engineering where I focused on using microwaves for reduction of nickel laterites before I did my PhD at the University of Toronto. And the focus of my PhD was using microwaves for assisted comminution and ore sorting. And after completing my PhD, I was fortunate enough to work at Separate Mineral Systems for some time on that project where we continued to, do research and development on microwaves and comminution.
Awesome. We're so glad to talk to you today and really curious about, you mentioned you're currently working on a deep dive on a research paper and wondering if you can share the motivation behind your deep dive into microwave technology and comminution.
That's a great question. I would say it all started with my PhD degree at the University of Toronto. As part of that work, I was working with a consortium. Our team name was Can Micro, and we were involved in this government challenge called the Crush It Challenge. And the idea was that a company or a research team would come up with a novel process to save energy and comminution. And our approach was using microwaves for assisted comminution and ore sorting. So as we know, we need more metals in our society, but we have to do this in a way that can result in less CO2 emissions and less energy consumption, and also an increase in metal production. And with this, with microwaves, you can actually accomplish this. So after finishing my PhD thesis, I was continuing on with this work, and I really wanted to figure out all the research entities that were involved in microwave assisted comminution. And that has resulted in us working on a review paper, which is very comprehensive.
In previous conversations, you mentioned that when you first started this project, there was a lack of public research published that was available to you. And how does that lack of public research impact your decision to compile existing studies on microwave technology?
I would say that there is a good amount of research, but most of the research we see today reference, papers in the last 5 to 10 years. And I would argue that there are many historical papers from the 50s, 60s and onwards that have fundamentals that we need to be aware of, to develop our baseline. And because of this artificial research gap, as I would call it, a lot of people aren't aware of these papers. So I think it's critical to, review all of the relevant literature and, to compile it in a review paper.
So how do you go about doing that when most of the papers out there in the last 5 years or so? How do you go back more historically 10, 20 years ago? What was the process you undertook to compile all of that research on the technology?
This was actually a significant challenge because I was doing many experiments while I was doing this literature review, and the literature review never really ends. The first strategy I took was using Google Scholar. That's a very good way to get research papers, especially journal articles and theses, especially master's and PhD theses. But if we want to, be aware of all the different work that's going on in the world, not just in our respective countries, we need to make sure that we look at the conference publications. We need to look at, articles from, before the internet, so before the 1990s. So I had to, use Google Alerts to be aware of any new literature that was coming out, connect with people on LinkedIn, as well as connecting with people on ResearchGate. And that's a big benefit of this work, is that, 5 to 10 years ago, you wouldn't be able to connect with someone from another country via ResearchGate or LinkedIn and share your research with them. So as I was able to get more papers and get more comfortable with the different researchers in this field, I was able to develop my knowledge base, both from a fundamental and applied perspective. So to this day, I still continue to, seek out others and share ideas, as well as gather as much information as I can.
Yeah. So in all this research that you're doing, is there any trends that stood out for you?
Yes, I would say there's, a lot of fundamental studies from earlier on that haven't necessarily been cited. There was one specific paper from 1991 by Walkowitz et al., U.S. Bureau of Mines, on microwave-assisted comminution. It's the most highly cited paper. It's been cited over 200 times. And I would say all the current literature these days make reference to this paper. But back in the early days, a lot of people were simply doing test work, knowing that it's not necessarily economic. So they wanted to show that microwaves can, in fact, be used for assisted combination. So in the 1960s, Kushner, 1966, was looking at microwaves for stone shattering. Other people were looking at using microwaves for excavation, um, to make tunnels. And now we see a lot of papers on mineral processing as well. So depending on the time period, the research is going to change. Another thing I would add to that is looking at novel, mechanisms. So as we introduce different sulfide minerals, which are in these ores, how do they actually interact with the microwaves? So the earlier papers didn't have answers to this. Whereas just about every single commodity has been studied, in one form or another. So there's an abundance of knowledge on fundamental ore interactions.
And, and what do you think, if any, the role of corporate NDAs plays in the lack of publicly available data on microwave technology and mining?
That's a really good question. I have to be careful how I answer this one. I would say, on one hand, we want to continue to develop our knowledge as a society and make progress, develop papers, but we also want to come up with processes as well. So, for an example, company A is doing all this work for 5 or 10 years. They try to commercialize their process. Unfortunately, it doesn't work out, and then all of that knowledge that they gained, just disappears because it's not published and it doesn't go into literature. Whereas another company might publish as they go, or a university might publish as they go. They don't necessarily reveal everything, but as they disseminate this information, other people can gain traction and push the envelope in their respective research area. Uh, some of the work that I've done has involved NDAs, and even just naming a specific commodity might give away the company. So we have to be very careful how we share the information and how we request this information. Some NDAs might have a 5-year hold, and as we know, someone might move from one company to another. They have all these wonderful ideas, but because they're tied in with an NDA, they cannot necessarily use that information or the strategies from their previous company in their new role. And in between government and industry, we also have academia. So there's many professors that, in addition to the research, they're doing work with the industry and they're also tied in with NDAs. So this creates what we would call a gray literature. So this data exists, but it's not accessible to the public. These reports are only accessible to the employees, and they cannot necessarily be shared to everyone. So it creates ground for competitiveness, but it also prevents some contribution and collaboration from taking place.
Yeah. So, as a researcher with a passion and a lot of study in the field, how much has that played into your desire and your passion and motivation for creating this database of publicly available information? Has that played in it at all, or how does that led you to wanting to create the database to share information?
Uh, Yeah, so the database was something I just thought about, a few months ago, and it actually stemmed out of this literature review paper because the review paper might have 300 references in it, but it doesn't have all the pertinent data. And because of copyright, we can't upload the papers from respective journals onto a single site. But what we could do is have a universal database accessible by all, no paywall, and it would have links to all the published conference papers, theses, journals, etc. So I think by having this database open to everyone, they can watch how the literature changes over time. They can access data. They can sort the database according to the ore that they're studying, the type of microwave system that they're using. Historically, magnetrons, have been the dominant type of way for making microwaves, but now we see the emergence of solid state. So it'll be very interesting to see how the literature changes in the coming years.
Awesome. So in your research, going back into looking at papers on the publications that were available that were done and experiments that were done in the 1950s to 1990s, how has microwave comminution technology evolved from like the 50s to the 90s?
So I would say, the 50s to the 80s is very experimentally based, but in the 1990s, you had the introduction of modeling, which is even more dominant nowadays. Depending on which country the paper came from and the, political tension at the time, that might dictate what their research agenda was. So going back to the 50s, 60s, 70s, 80s, you see a lot of papers from both Russia and the United States. But then as you look into the 1990s and 2000s, China has come in and they've been publishing an awful lot in this field. And in the background, Canada had a famous paper from 1984, The Relative Transparency of Minerals to Microwave Radiation from the Government of Canada. That's a very famous publication. So since that time, we've been in the background with all this work, but we see more and more countries, kind of jumping onto this research. So it's really starting to take off. And in my experience, the experimental work that has been done has been great, but we need to also add numerical modeling as well. And because these processes are very complicated, there's many process variables. We need to have the computational power to be able to do the modeling and then to do the real-time processing. And we actually have that capability nowadays.
You mentioned going back into research papers and looking at the research and experiments that were done going back to the 1950s, and that predominant microwave technology being used then was magnetron technology. What was your reaction upon discovering the first published work using solid state for comminution?
So I was really excited to see that. So I was, a student at University of Toronto since January 2017. Then I went to Sepro to do our pilot scale work in 2020. And then I found out about solid state. I learned about your company, Crescent. I learned about other companies that are doing this work. I researched it quite a bit. And I found that this technology is something that we need in microwave comminution because there's many things that we cannot achieve with magnetrons. In my work, arcing was a significant problem. Also, being able to, sweep across different frequencies, and also inputting a higher proportion of power from one single feed. So with solid state, that could be 4 to 6 times the amount compared to that of a magnetron. And the interesting thing with solid state is that there are very few publications in this field, but companies are very interested in doing large scale processing. So this might kind of go back to what we're alluding to before about publications and NDAs and work happening in the background. One thing that I would really like to see with this literature is comparison between magnetron and solid state for the same ore system.
Yeah. And if I can jump to Adam, can you just really high level give us the difference between magnetron and solid state technology, the differences fundamentally in technologies?
Sure. The big differences between solid states and magnetron systems are that, you're working off of a magnetron system is working off of a free running oscillator, which is the magnetron tube, and it's inherently not controllable in terms of frequency stability. The durability of it is much less because it's essentially a vacuum tube. So that's a factor when we talk to prospective clients and customers in the that are looking for our solutions, that we solid state systems can be inherently ruggedized to handle the mining environment. That's the reason why the defense in other demanding applications have shifted to solid state exclusively because of these high environmental loading conditions, I guess you'd say it, with vibrations and with temperature and other factors. There's a big difference on all the other big differences on solid state that make a difference in the mining sector is the high speed controls. John alluded to that with being able to control and manage arcing. Solid state can really react very quickly to that and adjust accordingly based on either perhaps even using AI to help manage that, or other algorithms. The high power systems, as Jon mentioned, we can deliver a lot of power through a single waveguide that is unmatched with magnetron systems. You can generally deliver about 100 kilowatts through a waveguide in magnetron systems based on what the current technology is for the tubes. And we can do 400 or 600 kilowatts through a same waveguide. That makes a big difference on comminution efficiency, because, and maybe Jon can comment on this, but the crux of it is the rapidly heat and the ore and leverage the discontinuities in that ore material, in that rock, to create the fracturing that's going on. And so rapidly heating and creating that thermal expansion is something that is, the more rapidly you can do that, the more efficient you'd be in the process. One thing that again, what Jon mentioned is the being able to pulse the power. And I think that's an unexplored capability with a solid state that we may find that there's some benefits to using that. We see that in other applications that we do outside of mining, where solid state, the pulse power capabilities of the systems is a benefit. A good example of that is in the plasma space, where pulse power is a desired mode to operate at. So one thing I'd like to add that as Jon mentioned about corporate NDAs, we are seeing some customers, even when they're bound by these NDAs, the clients we're working with do see the benefit to the broader humanity, I guess, if you will, on being able to get this technology out into the open. And so there's seems to be a little bit more willingness to even share what they know, to work with other partners outside of their companies. And that's encouraging in my mind, to start to maybe break down these corporate NDAs and bring in a bigger consortiums to do good work for humanity and move the process forward.
Yeah. So definitely, while we respect the NDAs, it's interesting just being in the research field that we want to share information, right? We want to share the innovation, the technology that exists. And I love the research that you're doing, Jon, that you've been here speaking with us today, just about what you've found and researched, and your knowledge and expertise. And I'm wondering, how do you hope that your research will influence future studies and applications of microwave technology, specifically for mining?
I think starting with the review paper that we're working on, it's amalgamation of over like a decade of my work. So I'm really hoping that myself and my co-authors can put out a critical review paper, but it's also a comprehensive paper to catch everyone up on what's happened in the past, what's currently going on, and what's going to happen in the future. And we want to be able to understand where microwaves fit in the mining value chain. So we focused a lot today talking about comminution, but we also have drying, we have high temperature processes in pyrometallurgy, such as calcining, roasting, smelting. So there's many different potential applications where we can use microwaves in the mining value chain. So I'm really hoping that the research that myself, my co-authors have done, and other people in the field can really push the envelope and allow the mining industry to finally adopt this technology on the commercial side.
Yeah, thank you. And Adam, what do you believe is the outlook in terms of business adoption of solid state?
I'm very optimistic about it. One of our best, some of our best clients are in the mining sector today, and we're hoping to grow that in the future. As certainly, we're in a development phase at this point in time, but I think that with success, we'll see many orders of magnitude increase in opportunities and in sales in delivering solutions to the mining sector. So I'm very optimistic and excited about the future for our technology in the mining sector.
Jon, any thoughts or comments on the future of using microwave technology, specifically solid state for mining? Any speculations on adoption?
I mean, I must have went to 4 conferences in 2023, and in each and every conference, they always talked about reducing CO2 emissions and increasing metal throughput. And through the work that I did with my team, we found that you can accomplish this with microwaves. As long as the energy source is clean, there's no off gases that are produced with microwaves. So, hitting that, 2050 net CO2 target is definitely possible. And some companies are even pushing earlier than the 2050 goal. So I really think it's just a matter of time before we see it adopted in the mining industry. In terms of the timeline, I couldn't say, but this is not the first time that people have been looking at this. There's been a few cycles in Canada where someone has gone forward with the project, made some progress, and then it didn't evolve into anything. But I think with solid state in particular, with pulsing, with this much higher power density, with proper process control, this is definitely an opportunity that needs to be taken advantage of.
Yeah. Thank you, Jon. And I know you're going to be joining us again for a second round of interviews where we're going to dive a little bit deeper. We're into potential applications beyond comminution and mining. We're going to talk about the sustainability piece of it as it relates to mining. And then Adam and I are going to talk a little bit more into Christian's field deployments of solid-state microwave generators. And we're going to get a little bit deeper into all of this in part 2. So thanks for being here today and talking to us with this overview. Really happy to have you join us and have this conversation and share a little bit more about microwave technology for use in mining and especially with solid state. So thank you, Jon, for being here.
It was my pleasure. Thank you so much, Lori and Adam.
Yeah, thank you, Jon.
All right. Tune in for part 2.